So I hope that we enjoyed the ice day on Wednesday. So class was canceled on Wednesday, and I decided that Wednesday's topic was reasonable to ask you guys to look through on your own. I don't know if people have had a chance yet to check out the YouTube video, but it's there as a resource. But I do recognize that we didn't have any time to talk about that class together. That class was all about taking the graph of a derivative. So all of these, I'm on page 16, by the way. This was the group activity from last class. Taking a look at the graph of a derivative, if this function right here is f prime, and then the goal is to graph f. That was the basic idea of last class. So did folks have a chance to look at this? And if so, were there any questions on the basic idea here? Okay, so then I'll just, okay. So then I'm just going to give the like 30-second highlights of if you have a graph of f prime, what do you do to graph f? So I'm going to write down very little here, but I'll say some stuff and you can take notes. You can check out this part of today's video after class. From here to here, the graph of f prime is always positive. Yes? It's always positive. I know it's tempting to call it decreasing, and it is, but that's not the first place to go. First thing to do is think about whether the graph is positive or negative. And all the rest of the way down here, f prime is negative. If f prime is positive, what is f doing? Dave, it is increasing. So you're going to draw something that is increasing for all of this purple amount, and you're going to draw something that's decreasing for all of the red, okay? The second question we have to ask ourselves, more than just saying is f, the graph that we're after, is f decreasing or increasing, we also need to decide about its concavity. Is it concave up? Is it concave down? What's going on? So the second piece of this puzzle is to think about concavity, and the concavity of f has to do with whether f prime itself is increasing or decreasing. So for this part right here in blue, what is f prime doing? It is decreasing. And it turns out if f prime is decreasing, then f itself is concave down. If f prime is decreasing, f is concave down. That fact is written like the page before this one. I think it's fill in a blank. But for all of that blue part, the graph of f is concave down. And then if we look... for the purple part, it's going to be increasing at a slower and slower rate. Yes, increasing, concave down. No, blue is all the concave down part. Purple to red is the increase to decrease. And then in this little section here, what is f prime doing? It's increasing. And if f prime is increasing, then f is concave up. It's just a fact. Think about it, stretch your mind a little bit, and it will become clear to you that that is true. And then we'll draw again in blue. This part of f prime is decreasing. So out there, f itself is concave down. Okay, there's a lot of stuff to wrap your mind around, but I'd encourage you to push yourself a little bit and see if you can make those connections if you haven't had the time yet to do so. Okay, so with that part done, we move on to, I think we're on page 18 today. Yeah, right there at the top of page 18. And we will take a look at first a quick announcement that has nothing to do with this class, but UMass Amherst would like to extend an invitation to join them for their upcoming career blast. Jump down to this part in red. With approximately 140 employers currently registered, they are expecting record numbers this year. So I don't know anything about this event other than this piece of paper. My guess is that it's just an event at UMass where folks like you guys go and meet potential employers. And I don't know if it's as formal as bringing your resume. It wouldn't hurt to do so, but you meet a lot of different employers and make some connections and maybe get some business cards and give your information to people if it seems like there's a good fit happening. So if you're looking to join the workforce or change jobs, this might be a good opportunity for you. This event is happening in February. It's Wednesday, February 20th, 10 to 3. I don't think you need to be there the whole time. I expect it's a drop in and then there's just all these tables around and you walk around and then leave when you're done. If you want to know exactly who is going to go, the companies that are going to go, there's this website right here, umass.edu/careers. I believe this was sent to the student body, but I don't know. All I know is that I got it the other day, so I'm sharing it with you. I don't intend to share it with you again the week of February 20th. So if you have potentially interest in this, write it down, check your email, or ask me. I can email you this document, and you can go. Any questions about any of that? Okay, so the next thing we'll do is take a look at the calendar, and then we'll dive in and start doing some math. So the calendar here, today, February 1st, it is our fourth class, although we missed class number 3. Project number 1 is due, so hopefully it's in the folders right now. If you don't have project 1 yet, I do accept them late, but there are penalties associated with turning the project in late. I'll go with whatever my syllabus says. I will tell you what I think my syllabus says. If you turn it in on Monday, it's a 5-point penalty. If you turn it in later next week, it's a 10-point penalty. If you turn it in after next week, it's a 100-point penalty. So there's a big drop, right? You really want to turn it in within the next week. But see if you can finish it if it's not already done. And this weekend, enjoy, because on Monday, we have our quiz, and then project 2 is assigned. So this is the little calm before the storm. Our very first quiz is on classes 1 through 4, everything up through and including today. That's on Monday. Any questions on the calendar? Okay. I haven't thought about the days of the week it lands. I can tell you that the next quiz is February 13th, which is not a Monday, so it's going to vary. Yeah. Okay, in terms of preparing for the quiz, since this is our first one of the semester, you're going to go through all the old homework assignments, all the old questions of the day, all the old reading, all the old stuff we've done in the notes packets, and all the old group activities. Seems like that should be enough. If you want some extra time on the quiz, come 10 minutes early. We can start at 8:30, okay? Instead of 8:40. So show up a little bit early if possible, and you can get a jump start on the quiz. Also, just like last semester, you're welcome to bring in an index card to help you as you work through the quiz. You can write anything you want on this index card, front and back. So if there are formulas or theorems or definitions or problems worked all the way out start to finish that you want to put on there, you just put it, okay? I do have index cards that I'll have with me on Monday, and there are also index cards on the outside of my office door. Math Studio has them too. Thank you. Josiah. Last semester, yeah. Just what are we doing here? Good question. Are we allowed to use the reference sheets? There is a reference sheet that I'm giving you for the first test. Okay, so let's go ahead and say yes on the very first page of this packet, and you guys should all thank Josiah because I hadn't thought about this question before. So you can use this very first page of the packet on the quiz. So rip it off on Monday morning and use it then. Okay, so let's move on. Again, I think we're on page 18. All right, here we go. Number 1. We will start with Sam. Okay, first thing to do is draw a very rough sketch. Sine of x without the calculator. The goal is to just draw one arch of sine of x. Sine of x start at the top, middle, or bottom. Sine of x up here, here, or here. Starts in the middle. Okay, so here's our graph of sine x. If we want one arch, then it seems like we are stopping at this point right here, so we need to know the x value at that point. What is it? That is pi. And we're after the area inside of here. Can you write down the integral that represents that area? From where to where? 0 to pi. Function. So we're going to put sine x and then dx is just part of the notation. And dx is always there. It goes hand in hand with the integral sign. Okay, so that's the thing that we're after. Now, 2 classes ago, we were able to just type that into the calculator, and it gave us the area, and that's fine. We'll move on to number 2. Todd? I want to chat with you right after class. Okay, so let's, before we actually focus on the specifics of that technique, finding an antiderivative of sine of x, let's be clear that that's actually what this problem is asking us to do. Here's a formula that we have seen and hopefully we believe. If you are finding the area under a derivative curve, what you're actually ending up doing is finding the total change in the original function. The derivative of f is the thing that you're graphing and finding the area. Turns out that represents the total change of the function. So in our case, what is f prime in this purple expression? F prime is sine of x, right? So f prime is sine of x. If we could somehow just get our hands on a formula for f, then we could just plug in the 0 and the pi and get our answer. So the goal is to find the f if f prime is sine of x. Said another way, find an antiderivative of sine of x. So let's get it. F of x equals. Okay, somebody took a derivative of something and got sine of x. It feels like it should have an awful lot to do with the cosine function, right? Derivatives of sine and cosine just flop back and forth. Is this right? No, it's not, because the derivative of cosine is negative sine. So given that there's going to be a negative that pops up that we don't want, we need to put something into this original f function to kill that negative before it comes up. What do I put in? I put in another negative. Right? You take a derivative of that thing, you'll get negative sine x, which is sine x. Okay, so that means, oh, great question. So we will talk about this kind of funny plus c at the end. It turns out for definite integrals, where we've got numbers on the integral sign, any antiderivative is fine. So negative cosine x by itself is okay. You can put a plus 17 at the end. That's okay. We'll talk about that detail later. So we'll come down here to number 3. Putting it all together, we've got this integral from 0 to pi of f of x dx is definitely f of pi minus f of 0. That's our fundamental theorem. So the integral from 0 to pi of sine of x is definitely, so what do we get when we plug pi into our antiderivative? Well, I'm just going to write negative cosine of, which number goes first, the 0 or the pi? The pi. Minus, because that's part of the formula, negative cosine of 0. Everybody see what we did? We have our antiderivative. We have the original f, it's negative cosine. We plug in the pi, plug in the 0, and subtract. Every time it's a subtract. Okay, again, without a calculator. Negative. How much is cosine of pi? It's negative 1. Minus. Well, okay, let's see. So 2 negatives cancel and make a plus. Cosine of 0 is 1. Altogether, 0. 2. So that's it. Now we're going to follow this process many times. We'll do a bunch of them today. But again, the basic idea is if you're trying to find the area underneath something, what you seek is an antiderivative. And once you have found an antiderivative, you plug in the top number, you plug in the bottom number, and you subtract. It's important to know top minus bottom because it's a subtraction problem. One surprising thing. What's surprising? So the area under this arch is 2. Is that surprising? That it's not 1.8743 or pi over 15? It's kind of strange that the area is exactly 2. But it is. Okay. Yeah, I'm still always surprised that it's a nice number. I cannot help you. Okay, number 4. We're going around to Josiah. Okay, so this was the question Cole had asked. Instead of saying f was really negative cosine x, we could have said, all right, it's negative cosine x plus 17, right? That's a perfectly good antiderivative of sine x. Because when you take a derivative of the 17, what happens to it? It becomes 0. So you can put any old number you want there, but gosh, it would be really challenging if the answer to what the area underneath this arch is dependent on whether you put plus 17 there or plus 4 or minus 8, right? Like the area is 2. So hopefully it doesn't matter whether we put a plus 17 or nothing at all. So what's going to happen? If we plug in, let's try the same calculation that we did right here. It's that thing right there. So I'm just going to write part of it, negative cosine of pi. But now, what do I have to stick on? Plus 17, because that's what I get when I plug in pi for my new function, minus, then over here, well, it's still negative cosine of 0, and then plus 17. And don't even worry about the cosines, but what happens with those 17s? Cancel, right? It's a plus 17 in the first one, then you subtract the 17 in the second one. So when we're doing one of these area calculations, and you're finding an antiderivative, yeah, you can put anything you want out there, but the convention is to put nothing because it's easier to worry about less stuff. So we usually don't put anything there. Okay, number 5, I'll go up to Angus. Okay, so again, the goal is to look at that and try to think of this 8x cubed as being an f prime. So the main difficulty in a problem like this is to find something whose derivative is 8x cubed. So some of you guys probably already have a formula, a way to figure out an antiderivative of 8x cubed. But even if you don't, see if you can just kind of piece through and come up with a function whose derivative is 8x cubed. Once you've got it, go ahead and plug in and check with your neighbors. Yeah. Okay, so what is an antiderivative of 8x cubed? 2x to the 4th. And then the goal is to plug 3 and 1 into that function right there. So we're doing f of 3 minus f of 1. That's the goal, right? And we'll come up with a nice way to write this notationally. But for right now, we just plug in. So 2 times 3 to the 4th minus 2 times 1 to the 4th is 160. So that's it. And that is an area, the area underneath the 8x cubed function. Between 1 and 3, 160 square units. Okay, number 6, Steve. Okay, so take a look at that next symbolic thing. It's the integral of 2x plus 3 dx, and I'm saying it's equal to x squared plus 3x plus c. So first of all, for the first time, this integral sign is missing what? It's missing the numbers. It used to be the integral sign with numbers means what on a graph? It means area. That's the only thing that the integral sign with numbers on it meant. It's the area. This is a completely new symbol that we are defining. It looks very similar to the integral sign that we saw before. It has no numbers. What is this symbol? It's not an area because there's no numbers, there's no boundaries that we can talk about. So what is it? It's an antiderivative. That's what this new symbol means. And at the moment, it really has nothing to do, although we've seen the connection here, with area. It's just the symbol that means find antiderivative of. That's it, okay? It has to do with an area accumulation type thing, but I mean, the reason we use it as a total area, that's interesting. No, it's not a like go minus infinity to infinity. Yeah, it's really just a symbol that means antiderivative, like independent of any geometry. Yeah. Okay, so again, that symbol, it is a brand new symbol for us. It means find an antiderivative. again, I'll highlight that the integral sign and the dx go hand in hand. You cannot have the one without the other. And antiderivative of 2x plus 3, do we buy x squared plus 3x? And even if we don't know where that came from, how could we check that this is the right answer? Just take a derivative. Derivative of x squared is 2x. Derivative of 3x is 3. The derivative of plus any constant is 0. So that's our general, just stick any old thing there. Garrett. Again, I don't have a geometry that's in my head to have units for, but I think you're right. I mean, like we do know what it should represent when there are limits and when it's an area. Yeah. For me, the dx just tells me what the variable is. When you guys take Calc 3, if you take Calc 3, the answer to this problem is very different from the answer to the first problem. In the second problem, the variable is y, which means x is actually what? A constant. So that whole 2x plus 3 is a constant, and the variable is y. So you might think about what that might equal, but not this semester. So we're going down to the next line. The process of finding antiderivatives is called integrating. So integrating, coming from the integral sign. Number 7, a lot of vocabulary associated with this new integral notation. The left-hand side of this equation down here is called an integral, the entire left-hand side. So we've got lots of pieces. We've seen the integral sign before. We've seen the word integrand to describe the function. The variable in this case is x. That's kind of what we were talking about up above where I changed it so the variable was y. This x squared plus 3x is the antiderivative, like the basic part. And then, as Cole had pointed out before, we stick on this plus c to be very general, because there's some unknown constant that could have been out there, and there's no way for us to figure out what it was. And if you wanted to read that thing out loud, that whole equation, the integral of 2x plus 3 dx is, or equals, x squared plus 3x plus c. All right, number 8, Dawn. Okay, so that c hopefully will remind you, right? Okay, so let's try number 9, finding two integrals. First is the integral of 3x squared dx. Second, integral of 3x squared dx from 1 to 2. Check with your neighbors as you do each part. Okay, what is the integral of 3x squared dx? It is x cubed plus c. Without the plus c, you will lose a point, maybe 2, depends on how many it's out of. But that plus c is mandatory. Every time you see an indefinite integral, that is without any numbers, there's a plus c going on at the end. Integral from 1 to 2 of 3x squared dx, well, it's different. So we're going to find our antiderivative. It's still x cubed. Do we need to put the plus c over here? No, because like when we put the plus 17, it just canceled. So it's fine to put plus c. It'll disappear at the end, so traditionally you don't put it. And now let's talk about some notation. Oftentimes, just so that we don't have to write that whole f of x business and f of b minus f of a, oftentimes you'll just put the antiderivative in brackets and then put the numbers on the right-hand side of the brackets. And this is our new notation that says plug in the top, plug in the bottom, and subtract. It's just a very compact way to say the right-hand side of that fundamental theorem of calculus. Or if it's just one term, you can get away without the entire brackets, but just put the vertical line. You're welcome to, it's really like one bracket. But again, we're so lazy. If we can avoid even 2 little horizontal line segments, we will. So vertical line at the right-hand side of the antiderivative, and then the numbers on the right. And that means plug in top, plug in the bottom, and subtract. So I can say this is equal to 3 cubed minus 1 cubed. 26. What did I do wrong? Oh, where did we go from 1 to 3? Thank you. Okay, 1 to 2. 1 to 2. 2 cubed minus 1 cubed. 7. Thanks. 7 is the final answer to that question, and I'm showing you how to write it down in a compact way. Yeah. Okay, and then just highlighting, big difference between these two integrals that looks almost identical. The integral, the answer to the first one is a function. It's a formula, x cubed plus c. The answer to the second one is a number. It's an area, okay? So really, really different things, even though the beginning part of the process is the same. Find an antiderivative. On the one hand, stick on a plus c and stop. On the other hand, you're going to have to evaluate the antiderivative at two numbers and subtract. So I recently found a website, because those plus C's cost points, like, and this is just not a, it's not just a GCC problem, it's like a national problem. So so x cubed, so number 7 down here is x to the 4th over 4 is the answer, but then in red is the plus C with some points subtracted off. So so how do you avoid that? You keep forgetting it. It's the plus C stamp with a little hole, so you can put it on your keychain. You just always have it. So it says just carry it around. If you're doing an indefinite integral, you just in an instant stick on the plus C. If you're doing a definite integral, this is better add the C just to be safe, but then there's a star. Don't do that because the answer will not have C in it. And then if you're at a restaurant, give the waiter or waitress a little extra plus C on their tip. It's very convenient. All right, next page. Number 10, and we were up to Joe. Thank you, Tiffany. Okay, the antiderivative of x to a power. We have to undo our differentiation formulas. So what's the derivative of x to a power? Well, you bring the power down, you copy the x, you subtract 1 from the power, right? We need to undo that and undo it in the reverse order. So the last thing I said was subtract 1 from the power. So what's the first thing we do to go the other way is add 1 to the power. So this becomes x to the n plus 1. The first thing I said was take the power and bring it down into the front, multiply by the power. So that's the last thing we undo. What's the opposite of multiplying by a power? Is dividing by that power. And you are dividing by that new power. And in fact, this is the one we'll write in English. Add 1 to the power. And divide by the new power. Okay, let's go over here to the right-hand side. Integral of 1 over x. Well, I kind of actually think we've already taken care of this because this is really x to the negative 1, right? I mean, I'm just rewriting it, right? 1 over x is x to the negative 1. So can we not just apply our rule here where we add 1? Yeah, if we try adding 1 to the power and dividing, what are we dividing by? 0, which is a problem. So this rule over here is only good as long as n is not what number? Negative 1. Right? That rule is fine for every power except negative 1. So we need a different rule. And it's really unrelated to the first rule. Where did 1 over x come from? It's natural log. Don't forget the plus C stamp on all these. Okay, e to the x is the derivative of some function. What is it? E to the x. That was the easiest derivative rule. That's also the easiest antiderivative rule. Stamp plus C. All right, a to the x is harder. Let's refresh our memory about the derivative. This would be something like 2 to the x. So what's the derivative of a to the x? It's a to the x times natural log of a, right? This is one that we didn't, maybe it's not as common, but we had it last semester. Okay, so then the derivative of a to the x is you copy the a to the x and then you multiply by ln of a. Well, we're undoing that. Okay, the opposite of copying a to the x is copying a to the x. What's the opposite of multiplying by ln of a? Is dividing by ln of a. So that's what goes over here. A to the x divided by ln of a. Okay, cosine of x, where did it come from? Sine of x. Okay, sine of x, where did it come from? It came from negative cosine. It's so easy to get those backwards. If we're going to have any hope with those two rules, or really any of the rules on this page, we need to know our we need to know our derivatives really well. We really have to know those derivative formulas if we're going to have any chance at going the other direction. What's the derivative of sine? Cosine. So then the antiderivative of cosine is just sine. That's the first one. Second one is tougher. What's the derivative of cosine? Negative sine. So the antiderivative of cosine, antiderivative of sine, we need to get an extra negative in there to kill the one that is about to appear. Okay, and then the last row here has some kind of general ideas. Derivatives over plus signs are really nice. If you're taking a derivative of x squared plus 3x, you don't even think about it, but what you're really doing is separating x squared and 3x in your mind. You're taking two derivatives and then you're adding them at the end, right? So if derivatives are nice over pluses, then antiderivatives are equally nice. So this is really the integral of f of x dx plus integral of g of x dx. And I'll never ask you to write that out in terms of splitting, but in your mind, you're going to just see a plus sign and say, okay, this is really two separate problems that I have to do. They're unrelated to each other. How about that constant multiple inside of an integral? We're going to bring it right outside. The plus c will come. We didn't actually do any antiderivatives yet, so they will when you do the problem. Right, so this last formula here, we said last semester many times, when you're taking a derivative, constant multiples, do they stay or go? They stay. Constant multiples stay. Well, for antiderivatives, constant multiples stay. You just put them in the front, wait until you're finished with the rest of the problem. So let's try 12 here, and in fact, I wish I would have put a little bit more into 12. So can we stick in front of this e to the x, can we stick a 2? Just in front of the e to the x one. And in front of the second one, we'll put a 3. So we're going to write this out in a little bit of detail, but again, I'm not going to require this detail, but just because it's the first one, I see a minus sign in there. That's a good thing. I can really do what? I can split it into two different integrals. So we're integrating 2e to the x dx, and we're also integrating 3x to the e dx. And what goes between? Minus sign. And then again, being really detail oriented, what can you do with the 2? You can take it out front. It's a constant multiple. See if you can do the same thing for the second one. So this becomes minus 3 integral of x to the e dx. And now we finally have integrals that are in our list. These two integrals are right up above. We just have to apply the rules correctly. So this equals, there's a 2, there's a times. Integral of e to the x dx from up above is e to the x. Yeah, and the plus c, we're going to stick 1 plus c at the end. Minus 3 times x to the e. It's up there. Which rule is it? It's the x to the n rule. This is x to a number. It's the very first rule we saw. And in English, we said add 1 to the power divide by the new power. Add 1 to the power, x to the e plus 1. Divide by the new power, e plus 1. And then yes, as Andrew points out, we do have a plus c that came from the first one and a plus c that came from the second one. They're really two different numbers. We just kind of abused the constants and grouped them all together in one plus c. Okay, second one looks a lot worse than the first and looks nothing like anything up above because this problem involves what operation? Divide. We have no rules up above for divide, right? Plus works great. Times c works great. Division doesn't work great. So there must be some like pre-calculus stuff that we can do with that to turn it into something recognizable. So first thing I see is one denominator and several terms upstairs, and I immediately think, okay, I can split this up into two different fractions. Downstairs for both, square root of x. Upstairs is the x and the 1. Yes? So I'm not saying that's an automatic thing to do every time you see one term in the denominator and several terms in the numerator, but you should know it's in your arsenal. You could use it. Now there is one notational thing that's missing now that I've split it up. That one fraction used to be a single term, but now it's two. We need to indicate that the whole thing there is with respect to the x. That dx needs to, in a sense, distribute. Okay, this equals integral. Okay, x over square root of x. You can mush those together and make a single x with a power. What power is it? It's x to the 1/2. It's really a couple of steps in one there, but you rewrite the bottom as x to the 1/2, and then subtract the powers. Minus x to the negative 1/2. Okay, and both of these things are in our list. If you see x to a power, you know what to do with it. You add 1 to the power, you divide by the new power. So what's the new power on this one? X to the 3/2, right? Add 1 to the 1/2, divided by 3/2. Yeah, so for me, I'll never write divided by a fraction. I'll automatically flip it over. Feel free to do that in 2 steps if you wish. X to the 3/2 divide by 3/2, which is the same as multiply by 2/3. Minus over here, x to the, add 1 to that power, 1/2. Divide by 1/2, same as multiply by 2. Last piece of this one, plus c. Questions on that one? Josiah, it's okay? No, the only over 3 part is the first part. The 3 came in, are you asking about this 3 right here? Yeah, so that 3 came in only because this guy became x to the 3/2, and the 3 is part of that one only. But really in my mind, I'm imagining taking one integral and splitting it into 2 different ones. We didn't write it down, but feel free to write it down until you're really comfortable with this idea. But it's really 2 separate problems that we just did. So the 3 is only in the first part. Other questions on this one? Okay, so this is a good time to maybe look at that sheet that you're going to be bringing with you to the quiz. It's the very first page. And we've got a whole slew of antiderivatives on this page. So for example, we saw x to the n. This is the same thing, but a different letter. It's a u. So the basic rule is add 1 to the power, divide by the new power. That's exactly what we got right here. We saw 1 over x. It became an ln. There's an absolute value. We'll talk about why that's there in a future class. We saw e to the u. I think I lost part of my equal sign. We saw a to a power with the 1 over ln of a. Right? We've seen a lot of these things. We saw sine, we saw cosine. We didn't see the secant squared, but that's okay. And you've got all these antiderivatives on the paper in front of you, okay? And then down below, constant multiples, you can take them outside. Pluses or minuses, you can split up, just like we've got there. Don't worry about the last 2 formulas for right now. We'll see them soon enough. Any questions on the reference sheet? Joe? It's on page 1 of the packet. Okay. All right, so let's come back here and then we'll do some group stuff. All right, so number 12. Note there are many integrals we can't get due. X times sine of x. Can't I just take this x outside like we did before? Just bring the x out in the front? I know. It's not a constant, it's a variable. It's really important to make that distinction. Under no circumstances are we ever allowed to take a variable outside of the integral. Constant multiples only. So what do we do when we have multiplication? One function times another. We don't know yet. Another multiplication, x times e to the negative x squared. Really not sure. And then e to the negative x squared. Well, the first 2 we will have a formula for. The next one, the last one, we'll never be able to do. It's not integrable, which is kind of disheartening, actually, because every formula I gave you last semester, I said take a derivative. Did you ever say, we can't? No, right? No matter how complicated. Do you remember that crazy complicated project with the ridiculous derivatives? It was Practice Makes Perfect was the name of it. Doesn't matter how complicated a formula is I give you, you can take a derivative. You just have to churn through the rules. It is very easy to make up formulas that don't have any antiderivative. That one right there has no antiderivative.
What does that say about the area?
The area exists. It's a perfectly well-defined area, and you can type on the calculator and get a decimal. But what I'm saying is we will never be able to find a formula where if you take a derivative, you will get e to the negative x squared. All right, so there are some challenge problems there. I'd encourage you guys to start with the group work on the next page, putting antiderivatives to work. 3 things you're going to do with each of them. There is an answer key that follows, and I'll walk around and help.